So, line of best fit, we might want to talk about that. Let's talk about charts and graphs. There's some do's and don'ts here. Let's talk about that. Scatter plots and two-way tables. So scatter plots goes along with this. So scatter plot and two-way tables. Flip the page. Equivalent expression simplifying. We did some of that. Exponential change. We talked about exponents, correct? This is where everybody nods their head. Thank you. Graphs of lines did that. Inequalities did that. Linear equations did that. Parabolas did that. Quadratic formula did that. Quadratic functions did that. Slope did that. System of equations did that. Zeros did that. Geometry, angles, circle, arcs, chords, radii, similar triangles. Now let's talk about similar triangles. We haven't done similar triangles, so we'll do a little bit of that. Okay. So let's first talk about line of best fit and scatter plot. What is a scatter plot? Scatter plot is when I give you a bunch of data, right, with X and Y, and you have to then plot it onto a graph, right? So if I have time and year and value of my automobile, or value of, not mine, but value of certain automobile. Okay? So which way do you think it's going to go? Which way do you think the scatter plot, what do you think the scatter plot's going to look like? In general. Down, right?
Down.
It's called what?
Depreciation.
It's called depreciation, right? So if I go ahead and plot the data, you would expect it's going to look something like this, correct? It has a general negative trend, right? It has a general negative. So we'll call this a negative correlation. Negative correlation. So correlation, the factor, you're not going to see this on the SAT, but there is a coefficient of correlation where R value is going to be less than -1 and 1. If R is negative, it means it looks something like this. If R is positive, it's going to look something like this. It has a positive correlation, right? Okay. If it's positive. If it's 1, that means that it is exactly, precisely, it's on a one line. It's a linear relationship, basically, okay? Negative 1 would be the same thing, okay? So, between there, what it's saying is that if I drew a line of best fit, I asked you to draw a line of best fit, you would draw something that looks like this, right? And you would call it, this is the line that best fit or best represents the data here, okay? Right, and there's a way to go about doing this, okay, in your calculator. Some of you have learned this, some of you have not. Do you guys do linear regression at all? You guys do linear regression on Algebra 2?
I don't remember.
Okay,
We did a bit, I'm not sure.
okay, all right. So, don't be disappointed, you'll do it in honors pre-calc, so we'll do it this year, don't worry about it. So, the closer these points are to this line, the higher the correlation factor, the higher, so you get 0.9, 0.95, 0.99, things like that, all right? If they are wider spread apart, you get something like 0.5, 0.6. And then you get something like 0, where 0 correlation basically looks like this. And there's no correlation, right? Because they're just random all over the place. Okay? So this is your line of best fit. Where do we use the line of best fit? What do we use it for? What's our main goal in deriving this equation?
Is it to find the average?
It's to find something. Anybody tell me what? So basically what this line is here is for us to predict.
The slope.
It's for us to predict the value of this certain automobile as the years go by, right? Because not every year are we going to have a data point, right? There are years where I am not going to have a data point. This year, if I go straight up, see, I do not have a data point, right? I do not know what my value is. So since I do not have a data point, if I had a data point, I could just use that data and tell you at that certain year, right, at that certain year, I know exactly what my car was worth, right, because I have a data point. But if I don't have a data point, I have to somehow need to be able to predict this or guess, right? And I would guess this value right here, based upon the line of best fit. So the line of best fit is something that where you are trying to predict something where you do not have a data point. Okay, that's what line of best fit is for. Okay? Let's see. Scatter plot. We talked about scatter plot. Scatter plot are these little points here. Line of best fit. Okay. So, are there just one line of best fit? Or are there many? Or how does that work? Okay. If you look at the line of regression, this is called a regression line. In a regression line, normally you would go ahead and just plug it in your calculator. The calculator would spit out a regression line for you. Okay? But you can also just draw your own line, right? And say, well, this is my line of best fit. This is what I'm going to use. Okay? So yeah, you might not be able to accurately predict, right? But by the same token, you might not be that far off either. Okay? So guessing, predicting this also is called what? We also call this activity interpolation. Anybody heard that term before? Never heard that term before? Interpolation. So this is called interpolation because you are actually guessing using your line of best fit within the range of your data points, which is good. Okay, you always want to do that. You always want to infer or make a prediction within your boundaries of your data point. Because if I had a scatter plot that looked like this, and my line of best fit looked like this, and I'm going to use this line of best fit to guess something that's way out here, odds are it's not going to be all that accurate. Okay? And this here is called extrapolation. So interpolation good, extrapolation no good. Okay? You do not want to guess while you are outside of your data boundary. Okay? All right. Okay. So that's good for line of best fit. You guys didn't bring your calculators, did you?
I didn't.
Huh?
I have mine.
You have yours? You're the only one? Last time it was Natalie was the only one. Now you're the only one. Okay. Oh. Charts and graphs. Okay, charts and graphs. Let's do charts and graphs. Charts and graphs. 3 things not to do on charts and graphs. complicated?
Waste time.
Huh?
Waste time.
No. Remember we talked,
Oh.
you're in my stats class, right?
Yeah.
We talked about charts and graphs,
Mm-hmm.
right? We talked about the pie chart, we talked about the bar graph, right? So the three things that you are not to do is, first one is the broken graph, right? The broken axis. Okay, everybody seen this before? So let's say I'm drawing a regular graph, right? That's gonna look like this. And I have two. One is 20, right? And then the other second bar graph is going to be 60. Okay? 20 and 60. So this is what a normal bar graph would look like, and right? And you would have categories here. I'm not going to write it. I'm not going to make anything up. But 20. Let's say I had 20 and 60. Okay. A broken axis is when I break the axis off, and I'm going to actually start my graph at 10 instead of starting here at 0 like I'm supposed to. Okay. So what does this become now? From here to here is 20, right? But that's going to look like 10. Why does it look like 10? Because I started from 10, and it's 20, right? Over here is going to look like, this is 60, so this is 20, right? Do you see the difference here? Let me redraw it again. Let's say that 20 was like that. What happens when I do this broken axis? I tend to overemphasize the difference. Can you see that? It looks like this is really, really small. When over here it's like 1/3. If you look at over here, it looks like it's like 1/5 or 1/6. Right? So it's called kind of manipulating the perception here, right? Okay. So you do not want to do, so the first thing you don't want to do is have a broken axis. Broken axis is something you do not want to do. Okay. Another thing is that I can have the same thing here, right? But what happens if I do it like this? Again, we have the same effect here, right? Even though I do not have a broken axis, it looks like it's overly small. And why is that? Because the widths are different, right? Okay, so you want the same width. And the last one is when you're using pictographs. Do not use pictographs in your graphs. Okay, do not use icons. Okay, icons are pictographs. So I'm making a bar chart of number of PCs. Okay. And instead of drawing a bar graph that looks like this, I'm going to do a pictograph. And for each one, I'm going to have a little picture of a CPU. See that? Again, it overemphasizes the difference, right? Because this guy looks really huge compared to this guy. When if you look at here, it's not that far off. Okay? All right? So these are the three things that they will ask you, or they'll try to get you, or try to, when you're looking at graphs, they're going to look at that kind. They're going to try to create that kind of stuff. And ask you what's wrong here, or how would I change it, or that kind of stuff. Okay, so you do not want those three things when you're doing charts and graphs. 2A tables. stats book. Okay, let's say that I gave you a graph or gave you a chart that looks okay, so this is a chart of the people that were on the Titanic and their steerage. In other words, were they in first class, second class, or third class? This is the data that we were given is 197, 122. 94, 167. And 120, no, 151, 476. Okay? So, first class. You survived, died. So if you're in first class, 197 survived, 122 died. Second class, 94 people survived, 167 people died. Third class is like this. Okay? So the question is, if you had survived, okay, what are the chances that you were first class? And how would you find them? Huh?
Put it in a fraction.
Okay, what kind of fraction? We're going to put in a fraction, but it's going to be a proportion. So what is it? What's the answer?
197 over 122. Oh, over all of them.
All of them.
Yeah.
So all of them, the number is 1207. I'll fill this number in for you here. It's 1207. So it's this over 1207?
And well, if it's in first class, it's 122. Right?
No, that's how many people died in first class. Well, okay, let's review the question again. If you had survived, what is the proportion, or what is the chances that you were in first class?
So it's 197 over the total of the first row.
Do we understand that? You understand what he said? So if I add these all together over on this, I'm going to get 442. This is the these are all the people that survived out of this, right? Okay. But listen to the question again, right? If you had survived, what is the chance you are first class? Right? So if you survived, so 442 people survived, what is the chance you are first class? So that would be your answer. Correct? What do you get then? If you were in third class, what is the chance that you died?
It would be 476 over the total of the third row over.
No.
Or it would be the other way around. 476 over 150.
No. If you were third class, right? So you have to be in a third class steerage, right? So you'd have to add this together, right? 7, 2, 6. So there were 627 third class passengers, and and I asked what are the chances that you survived, so it'd be 151 over 627, correct? Right? Am I good? Okay. Now I can also ask a question like this. I can also ask, out of all the people that were on the Titanic, right, what are the chances that you were in first class and you died? Now this is a little different, right? Because there's no ifs here, right?
122 over the people in the Titanic.
Correct. 122 over 1207. Right? So there are several different ways that I can give you a table and ask you these type of questions. You have to be able to think it through, asking what are they, am I adding the rows, am I adding the columns, or am I looking for the total? What am I looking for here, right? Okay, so you need to be able to discern what is what they're actually asking at that point. Okay? All right. TUI table. So the first ones that we talked about are called conditional probabilities, because I'm giving you a condition and then asking you a probability. So it's based upon something that happened already, right? Something has happened. Given that something has happened, what is the probability? It's called conditional probability. It's also called marginal relative frequency. Okay, and you'll talk about that in statistics. The thing that we talked about at the very end, you know, the 122 over 1207 is joint relative frequency, and you'll talk again, you'll learn that in statistics. Okay? So that's two-way table. Okay? So two-way table is, again, you have to just make sure they're not tricking you out here. Okay? That's two-way table. Similar triangles, similar triangles. Two Ds. So what are the similar triangles here?
A, B, E, and A, C, D.
Okay. So it's A, B, E. Is similar to A, C, D, right? Okay. So is this correct? Because ADC is the same triangle, correct? Can I say that? Okay, I see some of this, I see some of this. Okay, so when you're doing similar, or for that matter, congruent triangles, okay, when you're making these type of statements, if you're making a statement here, they have to correspond to each part. So each part has to correspond to each part. In other words, from here, in this one, BE has to be the same as DC. So BE, okay, is not DC, it's CD, correct? All right? So you have to keep them in order. Okay? So the short answer is no, you cannot do that. They have to, each point has to correspond to the same point in the other triangle. Okay? So, let's say that this was 7, this was 2, so this would be 5. Find CD for me. How would I find CD?
Would be 5, wouldn't it? Because
The same?
isn't that what the
It
arrows?
looks like it's larger than that.
Oh, what are the arrows meaning then?
They're parallel.
Oh, okay.
Probably like 6, 7.
guessing here?
Yeah.
Okay. So, this triangle and this triangle are similar. So this to this would be this to this. Can you see that? Right. 7 to 9 would be 5 to x. Right?
Yes, you're right.
Huh?
I did it.
Okay. Oh, you said 6. 6.5. Yeah, pretty close.
I said 6 or 7.
Oh, you said 6 or 7. Oh, okay. All right, so that's that. That's good. So that's one question. So the thing is that they're going to give you this little short thing and try to trick you out because you're going to say, oh, a 7 to 2 is 5 to x, right? Which is incorrect. Okay. And let's say this is 7, this is 10. If this is 3, what is x? How did I figure this out? This to this is this to this, correct? Right? So AE to EB is the same as AD to DC. So I have x to 7 is equal to x plus 3 to 10. Right? Again, they give you this little short little thing, right? But you have to be able to understand that it's x to x plus 3. Okay? So I'm going to get x over 7, x plus 3 over 10. 10x is equal to 7x plus 21. 3x is equal to 21. X is equal to 7. Huh. Okay. Makes sense, right? 7 to 7, 10 to 10. I got lucky there. Okay? You see that? All right. An easier question looks something like this. An easier question, a version that's a little easier than this would be right? And I would say 5, and I would actually give you the total and say that is 8. And I would say this is 6, what is x? Right, then you have to say this to this is this to this, right? So it would be 5 to 6 is equal to 8 to x. 5 over 6, 8 over x, 5x, 48. That's equal to 48 over 5. Okay, so this would be an easier version of that same question. Okay. Similar triangles. Any questions on similar triangles there? Pretty good. Feeling pretty good on that. So let's take a quick 5-minute break and then we'll go over geometry.